COVID-19 has penetrated almost every corner of the globe, causing a tremendous amount of chaos. The world has not faced this type of adversity for many years. It has crept in everywhere and has been devouring lives, moments, hopes. It has put us in a scenario that no one has ever envisioned. It has led us to a nightmare whose end is nowhere in sight.
Let's not make it sound like we're doomed, because seriously, there's a lot more reason to be optimistic. Look around you. See how colorful this world is, how bright life is. We don't need to live in chaos. Life goes on, learning goes on. Life is meant to be enjoyed with colors, and that's something we'll talk about this time. So buckle up as another exciting lesson is about to unfold. This is Teacher MJ, and this is DepEd TV. Before we start, let's test your knowledge about today's topic by having you answer these questions.
Which has the highest energy among the colors of the rainbow? A. Green. B. Orange. C. Red. Or D. Violet. The correct answer is D. Violet. Among the following colors of the rainbow, which has the least energy? A. Green. B. Red. C. Violet. Or D. Yellow. Right! B. Red. Which property of light enables the formation of a rainbow? 1. Color separation. 2. Dispersion. 3. Reflection. 4. Refraction. A. 1 and 3. B. 2, 3, and 4. C. 1, 3, and 4. And D. 1, 2, 3, and 4. B. 2, 3, and 4. That is correct. Which of the following colors of light bend the most? A. Indigo. B. Green. C. Orange. Or D. Violet. Very good. It's D. Violet. Which color has the shortest wavelength? A. Green. B. Red. C. Yellow. Or D. Violet. Again, the correct answer is D. Violet.
Look around you. Have you noticed that the things your eyes see have colors? They are beautiful, right? But do you know that there's a lot of science going on behind that beauty? The colors we see are part of the electromagnetic spectrum, specifically called the visible spectrum. So what makes us see particular colors? That is because objects absorb or reflect wavelengths of light.
The spectrum of colors ranges from violet to red, and each color has its own specific wavelength. Red has the longest and violet has the shortest.
We are all familiar with the cliche, the rainbow comes after the rain. However, did you know that there is a more scientific way to appreciate these colors that we see after it rains? Have you ever wondered how a majestic rainbow is formed? Why do we see spectacular events in the sky like a red sunset, a blue sky, rainbows, and many more? How is the arrangement of colors determined by nature? This time, we will learn one of the characteristics and properties of light, which is refraction, and specifically the dispersion of light. We will also try to find the hierarchy of these colors of light in terms of frequency, wavelength, and energy. To give you an idea how this phenomenon happens, let's do the psi experiment. While we are doing our experiment, please observe what happens and record your observations in your notebooks.
In this experiment, we will need the following materials: a flashlight, a big bowl, water, a small mirror, and paper. First, fill the big bowl almost to its rim with water. Next, place the mirror with a part of it partially submerged in the water. Then hold the paper above the bowl with one hand and use the other hand to turn on the flashlight or any source of light into the submerged part of the mirror. Finally, adjust the position of the mirror until you see color bands on the paper.
That was a very exciting experiment, wasn't it? Now let's check your observations.
What happened when the light hit the mirror? Did you have a different observation? Clearly, when the light hit the mirror, there was a reflection of light that occurred. Now enumerate the colors based on how they appear on the paper from top to bottom. Let's do it together. These are red, orange, yellow, green, blue, indigo, and violet.
Were you able to capture how colors are produced from the activity? Were you amazed by how the rainbow colors appeared on the paper? Light is a kind of energy that can travel through space in the form of waves. Light from the sun looks white, but it is really a mixture of many colors. The colors in white light are red, orange, yellow, green, blue, indigo, and violet. The arrangement of colors when dispersion happens can easily be remembered with the acronym ROY-GBIV. What is dispersion, by the way?
Dispersion is a kind of refraction which provides colors of light. When we say refraction, it is the bending of light from one medium to another. This phenomenon is observed when white light passes through a prism. A prism is a transparent optical instrument with flat and polished surfaces that disperse light. It can be made from any transparent materials like glass, plastic, or fluorite. Water in a glass can also act as a prism. It also breaks white light into the following constituent colors, namely red, orange, yellow, green, blue, indigo, and violet.
Now that we've learned the arrangement of colors of white light, it is time for us to dig into how colors of light are arranged in terms of energy. Here's a table that shows the wavelength, frequency, and energy of light ranges. Look closely and answer these questions. Which color has the highest frequency but has the shortest wavelength? That's right! It is the color violet, with a frequency of 675 to 789 terahertz and a wavelength of 380 to 445 nanometer. Which color has the lowest frequency and has the longest wavelength? Correct! It is the color red. Red has a frequency of 400 to 484 terahertz and a wavelength of 620 to 750 nanometer. The frequency of light waves refers to the number of waves passing through a certain point in 1 second. Frequency is generally measured in hertz, the unit of cycles per second. Wave frequency is related to wave energy. The more energy there is in the wave, the higher its frequency. The lower the frequency, the less energy there is in the wave. Within the band of visible light, the different wavelengths are perceived by people as different colors. As we mentioned earlier, the shortest wavelength is violet and the longest wavelength is red. Have you ever wondered why things underwater look different compared to when you look at them from above? Have you ever observed that a coin looks bigger than how it is originally when you put it inside a glass of water? What do you think happens in these cases? It is because of what we call the refraction of light. As we said earlier, refraction is the bending of light when it travels from one medium to another. When light crosses the boundary of two media of different optical density, a change in speed takes place. What is optical density? When we say optical density, we refer to the measurement of a component's ability to slow down the transmission of light. This change in speed is manifested by the bending of the light ray. To better understand the concept of light, we can relate it to things we often see. This is observed when we partially submerge a pencil in a glass with water. As you can see, the pencil appears broken or bent at the boundary between the air and water. Is the pencil really bent? Of course not. The reason why it looks bent is because the speed of light in water is different from the speed of light in the air. In that case, refraction happens. The index of refraction of a material is a quantity that compares the speed of light in a material to its speed in a vacuum. To understand this, take a look at this illustration. In this illustration, light travels from the air to the water. When the light enters the water, which is denser than air, it slows down and it is bent. Observe that the angle of incidence is greater than the angle of refraction. You can see that the light ray refracts or bends towards the normal line. Thus, light bends towards the normal line when traveling from a less dense medium to a higher density medium, and light bends away from the normal line when traveling from a denser to a less dense medium, like when a light ray leaves the water. The incoming ray from medium 1 is called the incident ray,
and the outgoing ray from medium 2 is the refracted ray. And the associated angles are the angle of incidence and the angle of refraction. When light enters a prism, its separation into 7 different colors is observed. The refractive indices of the different colors of light indicate that it travels at different speeds in the prism, which accounts for the different degrees of bending. In terms of the frequency and energy of colors, blue, indigo, and violet are the ones with the highest frequency and energy. These colors are the ones that are bent the most. At the end of the spectrum, red is the one with the lowest frequency and energy. It is the color that is bent the least, while violet is the most bent. Wow! That was a very interesting topic for today. I hope that you've learned a lot from our lesson. To test how much you've learned, let's do the Psi quiz. Which has the least energy among the colors of the rainbow? A. Green, B. Orange, C. Red, or D. Violet? The correct answer is C. Red. Violet is the color that is bent the most among the 7 colors because it has the A. Highest frequency, B. Lowest frequency, C. Longest wavelength, or D. Shortest wavelength. Right! It's letter D, shortest wavelength. Which of the following can separate white light into 7 colors? A. Cloth, B. Concrete wall, C. Cardboard, or D. Prism? The correct answer is D. Prism. What refers to the splitting of white light into 7 different colors? A. Dispersion, B. Refractive index, C. Reflection, or D. Refraction? Right! It's the letter A, dispersion. The refractive index is the ratio between the speed of light in a vacuum and the A. Speed of light in a vacuum, B. Speed of sound in a vacuum, C. Speed of light in a medium, or D. Speed of sound in a medium. The correct answer is C. Speed of light in a medium.
Did you get a perfect 5? That's awesome! I hope you had a colorful day with this learning session. This is your teacher MJ. See you again in our next episode as we explore, discover, and enjoy life. This is DepEd TV. Keep safe everyone. See you next time.